is generated over directed acyclic graphs. You know now how they look like. They are simple single response regressions. They would be called multiple regressions if we have only quantitative measurements. They are usually logistic regressions for binary responses. And in the very special case that I used to introduce the different types of structures, they are also linear in probability models, for instance. But they can be more complex things. And then an important question is, what is a factorization good for? Well, it has this beautiful feature that typically, when we don't have complicated additional constraints, like the regression coefficient in equation 1 has to be equal to the regression coefficient in equation 4, or things like this. When that happens, estimation becomes complicated. But if it doesn't happen, then this factorization assures that even very large systems can be estimated by standard tools. Logistic regressions, linear regressions, including possibly quadratic or interactive effects and so on, or other types of regressions. Regressions are used very generally for conditional distribution. So, and here's now my smallest directed acyclic graph that I can use to introduce the typical types of different types of dependencies that show up in different types of V's in a graph. And I can introduce to you the edge matrix. The edge matrix of a directed acyclic graph is this triangular thing that has zeros and ones. Below the diagonal, it has only zeros. So if you see, whether you see this or the graph, once you're used to handling them, they give you precisely the same information. The edge matrix tells you variable 1 depends on 2 and 3. Variable 2 depends on nothing. Variable 3 depends on 5. And 4 also on 5. So, and the general form of such an edge matrix is, if you have a parent of an offspring, then you see a graph, an arrow in the graph, and it has a 1 in this edge matrix. The edge matrix is a tiny little extension of the standard term used in graph theory, which is called the adjacency matrix, which things are adjacent. And why do we have this identity matrix added here and introduced a new concept? Not just to make you angry, but because it has nice features. You can then multiply different components of the edge matrix together, and it gives you interpretable results that you would not get with the adjacency matrix alone, because that thing has zeros along the diagonal. So, and this little graph is enough to show you the different types of V configurations. The first I have already shown you on the blackboard. It's a collision V. It's called a collision V. One of our colleagues was so friendly to call it also the Wermuth configuration because he thinks I'm an aggressive person. And the transition V is showing, well, you have an explanatory variable. It doesn't have a direct effect on the response, but you have to have a transmitting, something that sends the information to the response. And so it's called a transition V. And the last one is called a sink or a source V, because you have a common explanatory variable to two outer nodes. So, these are the three types of configurations V's that can occur in a DAG, in a directed acyclic graph. And one of the things that is so beautiful about graphical Markov models, especially the regression graphs, is that you can work out the consequences when you or somebody else who has the same data conditions on a variable you haven't conditioned on, or has marginalized, has omitted a variable that you have in your system. And the simplest way to see what happens is when you have a collision V, it remembers the starting points. What you introduce is an edge in a graph that is just a full line when you condition on the common response. And the reason is that you really introduce a dependence among marginally independent explanatory variable once you have the information on the response. You want an example for this?
Yeah.
You want an example for this. In the United States, the education for females and the level of education are essentially independent in most Western countries. Gender and the level of education you can attain are independent, marginally independent. Then the salary you get depends on the level of education. It increases with the level of education. But in almost all societies, females get much less cash in the end. So you have this V. And if you now go to a bank and look for the same salary, then you'll find many more females in the lower and many more males in the higher level. So you introduce a dependence. That is the V configuration and conditioning on the same response. The transition thing in the middle, that's obvious, and you probably would know it as if you work ever with physicians, they would say, I give something, I treat a patient, and the final response depends on whether he or she will follow my prescriptions or whether she'll not do that. So that is the transition thing. And the last one is often called in the literature, you have an unobserved confounder. If you ignore an important common explanatory variable, you see an association between observed variables. And if there was already a dependence, it will get biased, it will get changed. So now I introduce a few more terms and speak of the generating graph, which is in this lecture always a directed acyclic graph, namely this particular simple thing. And now I can ask, if somebody had the same structure but analyzed it in terms of a log linear model instead of a sequence of logistic regressions, what would she see? She would see a dependence between 2 and 3, because in a log linear model you condition on all other variables. And you are in this situation here. When you condition on this guy, this introduces a dependence of that kind. And it remembers the endpoints of the V, so you get a full line. So that's what you see on the right. Now, if you want to ask, when this gets complicated, I don't want to do that by hand. You don't have to do it by hand. You use this edge matrix. And the edge matrix you can multiply together. You take the transpose times A, and then you take the indicator. You change every element that is not 0 into a 1.
That's beautiful.
Yeah, simple, nice. And by the way, there is a package in R that does it also for you in case. So here's another example. I want to know, what does this same structure imply for my pairwise relations, just looking at bivariate relations. And then one has to use 2 steps. One doesn't have to, but that's a neat way of looking at it. You first turn one speaks of a parent, and of everything that is in a line pointing to a response as an ancestor. So what the operation of the ancestor graph, it changes every ancestor into a parent. So the first thing you do, if you want to condition, to marginalize over everything, you see that 1, 3, and 5 form a transition V. So 1, 3, and 5 form a transition V. You marginalize over this because you want to look only at the bivariate association, and then you introduce what I call, to distinguish it from that, a dashed line, eventually, on the right. So first, you turn every ancestor into a parent, so you see that only 5 is an ancestor and not a parent. So it is turned, this middle arrow explains. And then the next step is you look at the remaining, this was the transition V, and now you look in this new graph that you have generated for the source, common source or sync V's. So what do we have? We have 3, 5, and 4. And 4. So I'm wrong. I'm stupid. Nobody complained. It should remember the edge, the endpoints. You have 5 and 1, so it should create an arrow. This would be 1, 2, and 3, and 2 and 3 in the previous, and it generated by conditioning a full line. Sorry for the nonsense, but sometimes it's good if one makes mistakes. What else do we have? Do we have another V? Yes, between 1, 5, and 4. 1, 5, and 4. They are both sync or source V's, so they introduce now a dashed line, 3 and 4, and 1 and 4. And that's how you get the induced. What does a structure that I see, which is a simple directed acyclic graph structure, imply for the covariance graph for Gaussian variables and for all bivariate relations in general? For my symmetric distributions that I just discussed before, you see a dashed line by a known zero in the correlation matrix of the binary variables.
So do you know how to get from covariance graph to the generating graph?
Well, once you have messed up your things, it's difficult to get back. You can, the thing that many people try to do, use machine learning structures on covariance graphs. And I don't think that is a good idea in general. For a Gaussian distribution, which barely ever exists in reality, except if you measure the size of the length of leaves on a tree or the circumference of heads of newborns, Gaussian distributions, in my experience, never occur in practice. So, yeah, in these cases, you can possibly do something. But here, you can't. So again, you have a very simple way. You have an operator that I will explain during the next lectures. You close all paths in a particular way, namely turn every ancestor into a parent, and then you use that inner product, replace everything that is non-zero by a 1, and you have the edge matrix of the resulting covariance graph. Now, if you have a larger, not just 4 variables, but a triangular decomposition, or an edge matrix that describes the graph equivalently, you just do exactly the same operations. That's all. So, just to give you an idea of the different types of simple things that happen. If you have that graph, you see you introduce an edge that we just discussed in the concentration graph and in the covariance graph. Concentration graph, each edge means pairwise dependence given everything else. Covariance graph, like in a Gaussian distribution, means just the bivariate dependence. Is that pair looked at alone dependent, yes or no? And this is what this thing implies. If I have a common explanatory variable, well, it doesn't have any ancestors that are not already parents, so nothing changes when I go there. And then I introduce a complete graph, a total mess. So if you see just a complete graph, unless you then have the idea by some explanations, maybe by design, in psychometrics, one designs questions and has whole questionnaires and hopes that a single explanatory variable, a feature, an ability of a person explains the relations among the observed variables. So if I have that, that would be the typical situation in an experimental design situation. You make, say, a 2 to the 4 contingency table in which you have the same number of observations. Then you automatically have mutual independence of these things. And then you look at the response. It doesn't matter whether it's discrete or continuous or whatever. And now here, there's again no ancestor, nothing happens. And if I go to that case, well, nothing happens either, because every dependence is already just a marginal dependence. So now I want to get to the thing that I'm really interested in, the general setup for regressions. And it's not a single response regression typically, but it may be. So directed acyclic graphs are a special subset or sub-model type of regression graphs when each y you see here in the sequence is a single response. But it may be a vector. It may be many different features. And why is it so important? In particular, when causal relations are being investigated. Suppose a physician gives you a medication against blood pressure, high blood pressure. It will never ever happen that only a single feature, a single parameter in your body reacts to it. There are several. And in the whole field of what is now called causal models, started by Don Rubin and Yuda Pearl, this is not being considered. They only use directed acyclic graphs. So one needs an extension to get to more realistic, possibly causal interpretations. So it is ideal when we have a cohort study. A cohort study consists of a group of people that you observe at a certain point, time point later, and so on. Always the same people. Multi-wave panel data is also called sometimes. But what is important here for these types of models is that they also are appropriate for randomized interventions. And I will explain to you what that is. And they even can be cross-sectional studies. Then the data really do not support the time ordering, but it's an hypothetical ordering that you use. And sometimes, in case-controlled studies, you really condition on a response. Children have a particular malformation. And then you look whether a particular hypothesized cause is present or absent for those that are cases and for the others that do not have that malformation, that are the controls. So, in a little bit of more formal definition, why do I have that already? I wanted to give you examples first. Anyway, now I have that, let's look at it. We combine the 3 different types of edges in these graphs. And it happens because we have a sequence of things: response, 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 another response. I call that U. And then I have a box that is the context variables or background variables. They describe when did the study start, what is it just for males and females, and so on. So you have a general separation into responses and another group of variables that just describes the conditions of the study or the intrinsic features of a person that is participating in the study. And then I call these pieces G1, G2, G3, G4, and they partition U, and then I have V. And then you have something similar as you had before, a factorization of the joint density for each joint response. you have dependencies on their past and a marginal joint density for the context variables. So G greater than J means that my joint responses in GJ are in the past.
They are all for the same group of people.
Yeah.
You are looking at different aspects of over time.
Yeah. So here again, repeated in words a little bit. A regression graph, well, it has a node set n. It tells you how many variables are in the system and or are studied. And it's now not called a DAG because it's only a DAG in joint responses. But it shows you a sequence of regressions, single or joint responses. And we have 3 types of edge in that graph. The context nodes are just modeled like a concentration graph that you saw before. There you don't have much information, and often in a concentration graph things look simpler. We saw already before that fewer edges were introduced in a concentration graph than in the covariance graph, also in the simple cases that I studied. Then between explanatory variables and response you have an arrow pointing from the parent to the offspring, and between components of a same response there are only dashed lines. So there's again at most one edge coupling node pairs, and we have a directed acyclic graphs in vector variables and 2 types of undirected graph. So look at this thing here. Maybe I should show you that first. So now suppose you have your n and you want to describe things in terms of dependencies and independencies. The notation, so actually I should have used, no, it doesn't matter. It's at this point it's okay. You just partition your whole variable set and you want to ask, is the subset A independent of B if I just condition on C? So you ignore D. And that the answers to this are called separation results. The first for general graphs were given by Yuda Perl and his co-workers. A second was given by Steffen Lauritsen, and more recently in terms of matrices Giovanni and me gave another one for directed acyclic graphs. And for the joint regression graphs, they are not around. The notation is due to Phil David for independences, and if we want to study, as I told you, in my experience, researchers out in the world want to know about dependences, and independences are only there to simplify things. And therefore we introduce a special notation to show there is a dependence. You have a fork and it catches these 2 things. So there's at least one edge between the set A and B when you condition on C.
It's quite new notation. The dependence, the fork.
Yes.
It's used?
Yes. Okay. So, look at this graph. This is an actual study of really healthy females who went to a general practitioner and were asked several questions regarding their childhood. And so it's a special case where I have 2 response subsets and a context variable set. So the context variable tells you how old the woman is, what her level of schooling is, and the family status means how well respected she saw her family when she was a child. And then in the middle you find sexual abuse. And my colleague Jochen Hart, who collected the data, always reported something like between 5 and 8%. But he never looked at females alone. When you look at this group of 283 females, it goes up to 15% that report serious sexual abuse, meaning penetration during childhood. And that means it must be even higher, because when they are young, when women are young, they try to pluck it out totally and don't even remember it, and then suddenly later it breaks out. So this is one of the shocking examples of doing good analysis where things happen. So anyway, then they look at the situation as a childhood. Was there a loving relation to the mother, as the grown-up woman remembers it? Were there lots of constraints? You're permitted to do such and such and nothing else by the mother. And role reversal is something that happens frequently when parents are ill, chronically ill. They abuse drugs, or alcohol. Then the child has to take care of the parent instead of the parent of the child. So this is the background of the study here. And now let's get back to the missing edges and the edges present in the graph. So if you see between S and U no arrow, no connect, no edge, then it means conditional independence given everything in the past. It is like a conditional covariance graph. You look at the pairwise dependence given everything in the past. Every edge is just and that also explains why at the first step you really can do like you do it in multivariate Gaussian regression, separate analysis of each component on everything in the past. It will not give you the totally precise maximum likelihood estimate, but for a first step it is really nice. So also we use typically the A and B are the only two discrete variables that are here binary. All others are age is obvious, is continuous, and family status has 3 levels, and the others are answers to questionnaires. So you see SU is independent of B and C. You see no edge, no arrow between U and A. That must mean given all possible remaining explanatory variables. So given R and everything that is further in the past. And here, when it is a concentration graph, you always have a missing full line if there's independence given all the remaining variables in that past. If you look at the context variables here, you forget about the future. It just describes what happened in the past. And so now if you see an edge, it is totally analogous. So no dashed line, you have a dependence given everything in the past. No, a dashed line present here. U and R must be an arrow present. Then you have the other explanatory variables in the conditioning thing. Everything that is in the past and the others that is there. And sometimes that can simplify even further, but for defining the structure that is good enough. So you see an edge there, then you have given the remaining variables a dependence or an independence.
Is it the mother's love? This one seems to should be. So this one is observed after this.
Yes.
Sexual abuse finding.
Yes. Although I mean, it's a retrospective study, so they all were asked when they visited a general practitioner because they had a cold or something harmless. But the time point, of course, this is family status and schooling during childhood, and we assume that the sexual abuse occurred later, and then this is the general evaluation by the grown-up, how she feels or remembers the relation to the mother and to the parents. Now I don't want to do that. Let me see whether I find my other examples, and I don't. I know, there's one. So, here I have already, I don't show you the first ordering, one usually starts with the ordering, but directly what happens after statistical analysis. And sometimes we use dots to remember that we have discrete or binary variables, and circles for continuous variables, because they are evaluated by questionnaires or actual measurements. You have quantitative measurements. So this is a particular study of how successful treatment of people is that report chronic pain. Every pain starts acute, and if it is being treated more or less directly, most of the time physicians can find the cause and you can get rid of it. The longer you wait and you don't get any treatment, the more chronic this pain gets, and then it spreads eventually over the whole body. You have pain almost everywhere. Here the site of pain, the starting site of pain is either head and neck or the back. So that is in some way also a discrimination between people with a higher level of schooling. Guess what type of pain they will have? Headache. And those who work hard outside, the workers, lower class people, they have backache because they ruined their back with hard work during their life. So we start as with a context situation of the level of formal schooling and the number of previous illness that is taken in chronic pain clinics as an indication of morbidity. Is it generally healthy and outgoing and still happy, or does she constantly complain about some type of illness, and that eventually leads to things like depression. Depression and intensity of pain are the two main features for chronic pain patients. And we look here at a study that started before a 3-week treatment in a clinic, and you measure as a joint outcome, because they measure two aspects of the same problem, namely you have chronic pain, depression, and extremely intensive pain that spreads over the whole body. And then you have a measure of chronicity of pain, not only how long you have had pain, but how many treatments did you get already? Did the pain start at a particular type of the body and then spread? It's a sum score of different things. And the site of pain I explained already. So you have joint responses before and after treatment. So it is a prospective study starting here and a retrospective study regarding the older variables. And if you would do just a single regression, let me see whether I have the picture already for the next. No, I don't. Okay, so we can do it without the picture. If you do a single regression of y on everything in the past, you just find one explanatory variable, ZA. It's not a linear relation, it is rather something that looks like success of treatment, and this is intensity of pain after treatment. So you get a known linear relationship, and the explanation really is that you have a lower, higher treatment success the lower the pain was which you started. And if after treatment you still have a lot of pain, well, you also don't report any treatment success. So that is an explanation of the known. You would not try to fit anything non-linear. But what I'm trying to tell you is, when you do nothing but a linear regression of y on z and z square and everything else, you find that there is no direct dependence on anything else except the intensity of pain after treatment. But what does this graph help us? This graph helps us to trace possible pathways of dependence. You have a lower level of formal schooling, then you are likely to become, if you get any chronic pain, a back pain patient. A back pain patient is helped less in this particular clinic regarding the intensity of pain, and the higher, and then you have this relation between intensity of pain. Though this means one has to, that you have a way of looking at the graph. Doesn't tell you how strong the dependences are, which direction the dependences are. You have to believe me at the moment. You have to have the whole output of sequences of regressions that lead to that graph. I can show you later. But anyway, it's a positive, it's this type of pathway that we can trace in the graph. And it would help us also to intervene. If it appears this direct relation from the site of pain to the intensity of pain after treatment tells us that whatever these people have been using in the chronic pain clinic, it helps the headache patients much more than the backache patients. And so something would have to be done there to intervene. And that is what the pathways in the graph eventually can tell us. And if we can derive these things formally, we are even better off. And we have reached quite some stage now to be able to do that.
The treatment is the same type of treatment?
The treatment in the clinic, yeah, it's the same type.
Same type of...
You have report.
It doesn't depend upon the type of the pains for a group of people?
No.
I see.
It's the same. So I really didn't want to do much more here now because it's getting us into, well, actually I can show you that thing. What we also, I have shown you before a few pictures where I said, well, I have a directed graph, a Markov chain. If I take all the errors away and do a corresponding concentration graph models, we have parameter equivalent things for the binary variables and for the Gaussian, and otherwise at least the same independent structure. So the first question for having the same structure is, are the set of independences defined the same? And we have developed graphical criteria to decide this. And for the data I've shown you just now, it is indeed true, nothing can be said about the first part, but for the last 5 variables, you see there is no collision V. The collision V's in a regression graph extend slightly what we saw before in the directed acyclic graph. The collision V there was just this thing. So if you condition on that, you introduce a full line. And in the regression graph, there are 2 other situations that can occur that would introduce, by conditioning on it, an error, and that last thing would also, by conditioning on it, introduce a dashed line. So in a regression graph, you then have more collision nodes, and all the remainings are called transmitting nodes. And in terms of these things, I will explain to you tomorrow. So when is it? Thursday. How you decide that really this is Markov equivalent to the first 2 sets on the last, and this also Markov equivalent to that. And what is the implication of Markov equivalence? Well, if you do machine learning strategies, you have no way of deciding with any statistical test between which the structure is really the one that is there. So you need the information that is available in a substantive field to decide between response variables and context variables. Sometimes it doesn't matter because the structure doesn't change, but often it does. And then it's important. Well, if we don't know, if we have an alternative system that is Markov equivalent, then we obtain a different interpretation. Or if we have that already as a hypothesis, but no program to do the corresponding joint response regression, then we can use that one to test that in a new set of data. And here, for instance, really you learn that switching the errors doesn't matter. It doesn't. There's another one, and when you switch the errors, there's no B generated. So that really is the same as up there. And the general result actually is as simple as that. If you have any regression graph and the set of collision nodes remains unchanged, it can change from this to that or to that, doesn't matter. Then the two graphs are Markov equivalent. It's so beautifully simple.
Now, so that kind of structure is proposed by some experts, or did you get it from data?
I always have. I'm lucky. I have been lucky in my life to work with people with whom I can discuss a lot, where I know how the data have been selected, and where they can tell me their first hypothesis that they have. And then it's a combination of these things.
So you have some skeleton from the group of people?
They know, for instance, well, that the family status in their previous studies influences both of these things. And then whether I add schooling and age that doesn't directly influence sexual abuse and family distress. What did I tell you? Family distress, that is things like
parents fight every day.
Yes, for instance, parents have chronic illnesses, parents use drugs, parents use lots of alcohol, stuff like that. That is family distress for everybody in the family. Okay?
And from your experience, is it it's like you have a hypothesis from the group of people?
Yeah.
And then you just...
I try to integrate the hypotheses that I have. And
you can modify the
yeah.
from
And then I look at the data, and sometimes they have to be modified, and sometimes they don't.
Okay.
I can try to find another one of my examples. Let's see. Well, it can give you an idea, at least, what we can do also with these graphs. Motivating is that now somebody else does an analysis, but doesn't have the information on, what is it, before treatment? No, both of them. Just not on the outcome ZA and XA. What will happen? Suddenly you see a direct dependence on two other variables. That is what you can derive by as an induced graph, as an implication of the first structure. And if you now ignore in addition A, then somebody else does regression on Y and U and B, and only on U, on B and V, then they will see this type of structure. So it's not what you induce, but it's comparing with somebody else who only has done a regression on Y, on B, and U, and V. And then suddenly he'll see a direct dependence appearing on U and one on V. Whereas the true structure was much, much simpler. There was no dependence. Once you have the information on how the treatment before and after, the main intermediate outcome, you know the illness has depression and intensity of pain before they get into the clinic as the main components. What is the intermediate outcome directly when they leave? The success of treatment is measured 1 year after they have left the clinic, because it is a general tendency of patients that they report lots of success the moment they leave the clinic. But if you ask them half a year later or a year later, it's much more realistic.
Why don't you show the 3 pictures on the same page?
What I can try to do is draw the picture on one. That. Where is?
You can just push it up.
How?
The blackboards move.
Oh yeah. That's faster. V U A so I have Y successive treatment, huh?
Yeah.
Then I have ZA, ZB, where that is intensity and this is depression. Then I have ZA, ZB before treatment, before clinic. ZA, sorry. No, something must be wrong. X, this here is X. XB, XA, XB, and this is ZB. And the others I have level of schooling. Should I write down the names as well? No. Okay. Whatever you like.
Then next page, so they can see.
Yeah.
Yeah. Okay,
That's better. Sorry, it doesn't fit on one page. Oh, well, maybe I should have tried to put it on one page, like the other figure. So, as I said, the only direct dependence is on intensity of pain after treatment in a non-linear way that I explained previously. If you ignore these, then what must happen? You marginalize over that and over that, so introduce a direct dependence of Y on V.
Yeah, I imagine that if I analyze the data, I think I can draw the arrows without the dashed.
Sure. That's another possibility. You can say there is something unobserved that we haven't studied in that particular case. So that is a generating process, a simpler generating process, including latent variables. But the thing is that you really can see that there will be a dependence. Whether that dependence is strong enough to be statistically significant, that depends on the individual strengths of dependences. Because take a correlation, 0.4, multiply it 3 times, what you see is the actual dependence of the response on the last variable. And that is a very small number. If it were 0.8, okay, it would still be sizable at each step. But in the social science context, the typical dependences, when measured in terms of correlations, range between 0.3 and 0.7. They never get extreme. Or they are taken out as missing because they are so weak that we don't want to have them in the picture. What is a strong dependence or a weak dependence depends on the context that you are studying. If you are studying a common cold, who cares? When you study accidents in a nuclear plant, very small dependencies may be extremely important. And the usual things regarding chronic illnesses and stuff and effects that you remember, the dependencies are, when you can express them in terms of correlations, neither very strong nor totally weak.
Now you seem to have a theory or tool that you can come up with the graph with the mixed graphs, so something like arrows and dashes and we have a program to come up with that kind of a structure.
All you need is simple regressions.
Yeah.
But if they're all categorical, you would use joint response regressions. You use the logit models by Gary Klonek and Peter McCulloch. If you have a joint Gaussian, it's totally simple. And if they are not Gaussian, but just you want to use, nevertheless, regression coefficients as for measures of linear dependencies, you can also include quadratic terms in your equations, and then you get nonlinear. You can detect nonlinear dependencies and so on.
Okay.
So there is no press a button and get the answer. Also, don't forget, sometimes there are several structures almost equally compatible with your data. That problem cannot be solved here in such context. I'm presenting you things with which the previous one at least, with which the substantive workers in the field were happy. They also liked that one can replace the dependence in terms of an additional latent variable, because it means they have to look for other explanations that they haven't included so far in their studies. So that's sensible. And then this is just an eye-opener. How different things will look like depending on how you analyze your data. It is over-conditioning or under-conditioning or whatever else can happen. Actually, I hope I get to this concept that we also introduced a little while ago. Everybody has heard, who works with applied people, about confounding. You have a dependence, then there's a common explanatory variable that you don't see, and what you see in the summary graph, it confounds, it may bias change the actual dependence that is here. So it may reverse the direction, so a positive dependence may be turned into a strong one. This may be as strong as the others, and you see an independence. Almost everything can happen. But this is only when you marginalize. You can already imagine that if you can combine conditioning that introduces a dependence and marginalizing, then also bias and distortions can happen. And we have named that indirect confounding. Maybe not the best name, but it is this type of confounding you can avoid when you do randomized interventions, so that you allocate patients to different treatment groups by just tossing a coin or doing another randomization mechanism. But indirect confounding is a problem also in such intervention studies. It doesn't go away. So that is a more serious problem that has been ignored by almost all statisticians until a little while ago, when Jamie Robbins and Larry Wasserman had their first example. And I hope I will discuss that with you in the next 2 days.
Okay.
So I was not successful in getting more questions yet. So on Thursday I'll get more questions in case you come. Don't worry, and don't worry about language or things like that. I've given up worrying about making mistakes in English long time ago. Because I traveled so much, and most of the countries, I mean, everybody has a different accent, and we are happy if we get to some understanding. And sometimes it's only hand and feet and somebody else who can translate. So don't worry about language.
They are thinking twice or 3 times. Yeah, they are thinking more than twice before they
ask a question. Yeah.
Ask a question. So
Yeah.
they are very careful. They are very serious.
Yeah.
Okay.
But you have to learn that asking questions is the only way to get the answers to the things that you didn't understand. And there are always things you don't understand, especially if somebody is running around here like.
Okay. Is there a question?